So when we started this problem, we said there's two things we have to check. We have to check impending slippage, and then we have to check impending tipping, and then we decide which one of these is smaller, and whichever one is smaller, well, then that's our answer. So now we're going to look at impending tipping. So we're going to say we're going to check tipping. And the question is, what would be a good way to start this question or this problem? And I don't know. I think I'll draw a free body diagram. That always seems like a good idea. Now, you're going to put the force on here, P. You got your weight coming down like this. And this dimension here is 1.5 feet and 1.5 feet. And then that dimension there is 4.5 feet, like that. And our weight, we said, was equal to 500 pounds. Now, when this guy tips, right after it tips, it's going to look like this. Okay? Because when it tips, it's going to be rotating about that corner right there. So my normal force will be right there. Now, if the friction force is 0, then it's not possible for it to tip, because there has to be something going back in that direction in order for it to tip. Otherwise, it would just slide. So there has to be a friction force here, which I'm going to call the force of friction, like that. And then, if you would like to, I'm going to call that point of rotation point A. Now, to analyze this problem, we want to look at the original free body diagram before the tipping occurred. So look at the black free body diagram there. And what we would like to do, and maybe before we do that, we should put our equilibrium sign convention down here so everybody knows what we think. And so I'm going to sum moments about A and set that equal to 0, like that. Now, this force P creates a moment about A, and that magnitude is P times 4.5. Put a minus sign on it. Then I've got 500 times 1.5. It rotates in the positive direction, so put a plus sign on it. And there's nothing else on there, see, because the normal force goes through point A, the friction force goes through point A. So it's only these two terms here are the only things that get involved with this equation. And so then this is equal to 0. And from that, it's easy to solve and see that 500 times 1.5 divided by 4.5, and let me get my calculator out here. I think I know the answer, but you can never be too sure. So 500 times 1.5 divided by 4.5, then this value turns out to be 166.7 pounds. So it only takes 166.7 pounds to tip the object. But it takes 200 pounds to slip the object. So you say, this may be the answer. And so all you have to do is you look at it and you say, P slippage is 200 pounds, and P tipping is 166.7 pounds. So if I start increasing this load, the second I get to 166.7 pounds, it's going to tip. And we never make it to the 200 pounds. So then The answer is right there. P max is equal to 166.7 pounds. And I'll draw a rectangular block around that. And you see, like with these kinds of problems, you never exactly know which mechanism is going to control. And there's, the way I've done it here is one way to look at it. There's, probably some other ways you could look at it. Like, for instance, had we done the tipping calculation first, then we could have summed in the vertical direction and found out what that normal force is. Once we know the normal force, we could have then calculated the required coefficient of friction, which would be 166.7 over the normal force, which we already know was 500. And we would have found out that the required coefficient of friction is significantly less than 0.4. So that would have led us to the conclusion that tipping would have been the failure mechanism. So there's a lot of ways to look at it, but just the easiest way, or the most, I don't even want to say easiest, but the most direct way and the way to not introduce a mistake is just to check this one and then check this one. And whichever one is the smallest, that's your answer. So it's just that easy.